Okay, so this just gives us a brief overview of the two different methods for proving two triangles congruent. We have SAS, which means that we have two sides that are congruent and a second pair of sides that are congruent, and then the included angle, which is to say the angle where the two sides meet, has the same measure on both triangles. And then we also have ASA, where we have a pair of congruent angles in the two triangles. Again, the tick marks tell us they're congruent. We have a second pair of congruent angles, and the side connecting the two angles in the two triangles is congruent. So that gives us ASA congruence. Okay, so the first problem we had here, we had to sort of look at some of these figures. And here we have that E is a midpoint. Now, it doesn't specify whether E is a midpoint of CD or of AB or of both. So let's start with the assumption that it's just for CD. In that case, we have that these two sides are congruent. We have these two angles are congruent because they're vertical angles. And then we have these two angles congruent because they're both right angles, and that would give us ASA. Alternatively, we could have said that E is a midpoint for all of these, for AB as well as for CD, and said that AE and BE are congruent. And then we would have had side, angle, side congruent. So we could have done either one here. Okay, for the next one here, we have that BC bisects angle ABC, and hopefully you saw or figured out that it should have been bisects angle ABD. And that means that we can say that these two are congruent to each other. And we also have that AB and DB are congruent to each other. So in this case, we have side, angle, and then we have this shared side, so we have these two are congruent by side, angle, side. Okay, for the next one, we have here that BC and BE trisect angle ABD, and what that means is that all three of these angles here are congruent, which, in other words, ABD has been cut into three congruent angles. We have that AB and DB are congruent. We have that AC and DC and DE are congruent. So what that gives us is side-side angle, which actually is not sufficient to prove that they are similar. Once we've established that AD is congruent to CD, that gives us our first pair of sides. From these two steps, we get that the angles are congruent. That gives us our angle. And then BD is congruent to BD by reflexive property in step 4. So now we can say by SAS that these two triangles are congruent to each other. Okay, moving right along. So here you are to prove that these two triangles, NPR and NTS, are congruent. Those are the two outer triangles there. And so we have this triangle being congruent to this triangle. And by the way, this should say angle 2 is congruent to angle 3. Yet another error. Okay, so we have 1 and 4 congruent as a given. So we have 1 and 2 are supplements, 3 and 4 are supplements. And the reason for that would be that linear pairs form supplements. And by linear pairs, we mean two adjacent angles. They share a ray, and together they make up a straight line. So we'd say linear pairs are supplements, and then we'd say same as 2 here. Okay, so then angle 2 is congruent to angle 3 because supplements of congruent angles are congruent. And so because we have that 2 and 3 are supplements of 1 and 4, which we already know to be congruent, we can say that 2 and 3 are congruent. Okay, we have PR is congruent to TS, and that's a given. Okay, so now what can we say? And we also have that NP is congruent to NT, and that is a given as well. And so we have these two congruent, and we have that PR and ST are congruent. So here we have side, angle, side. We have side, I'm sorry, we have that the triangle NPR is congruent to, sorry about the handwriting, to triangle NTS. And again, the sequence of the makes a difference in how we write this. So N corresponds to N, P and T correspond to each other, so they occupy the second places, and R and S correspond to each other, so they each occupy the third position. And the reason that we can say this, as we said, is SAS. And so we got an S in step 5, we got the angles in step 4, and then we got in step 6 the second set of sides. So we want to do this in the right order, SAS, SAS. Okay. Then we go on to this proof here. And the idea here is that we have that SV is a bisector of TSB, which means that these two angles are congruent. We have that VS is a bisector of TVB, which means these two angles are congruent. And we're supposed to prove that that triangle TSV, this should be, is congruent to BSV. And so we already have two angles. And so we can say that we have that, we're going to introduce our givens. So SV bisects angle TSB, that would be 1. 2 would be that VS bisects angle TVB, and these would be by givens, and same here. And now we can say that angle TSV is congruent to angle BV, I'm sorry, TVB, no, TVS, sorry. TVS is congruent to angle BVS. And the reason would be bisectors create congruent angles. And 4 would be the same. And then we have that SV is congruent to, and we'll say VS, and or we'll say SV. And that's reflexive property. And therefore, we can now say that triangle TSV is congruent to triangle lots of congruent sides here, and these two angles, because they're vertical, are going to be congruent. So we have one that we have to introduce that we have circle C, and that's a given. And the reason is we need to establish that C is the center point, otherwise we can't use radii. Okay, now we can have that or BC is congruent to AC is congruent to DC is congruent to EC. The reason radii of circle are congruent. Okay. And now we can also say that angle BCA is congruent to angle DCE. By the way, the order of points here does not matter. I could have said angle ACB is congruent to DCE, so that doesn't matter. That's reversible, unlike the order with triangles. Okay, and the reason here would be vertical angles are congruent. And then number 4, we would say that triangle B, or I'll say ABC, that's a B, believe it or not, is congruent to triangle EDC, and the reason for that would be SAS, and the steps are actually 2, 3, and then 2 again. Now, here I could have said ABC or BAC, and that wouldn't have mattered only because we have an isosceles triangle. Okay, and speaking of which, let's prove something about them. Okay, we're told that CE and CF are congruent, and we're to prove that angles E and F we're going to prove that these two triangles are congruent. Now, we cannot just use reflexive property for a triangle, because you could not say, for example, if you had these two triangles, A, B, C, and we had, let's say, that ABC, triangle ABC is congruent to BCA, and the reason is because angles A and B are not congruent. And so that's where we're saying that the order matters. A has to correspond to C, and we would not have that A and B in this case would be congruent. On the other hand, here with the isosceles triangle, that may not be true. We may be able to say that E and F are congruent, and in fact we're going to prove it. So first we have that CE is congruent to CF, and the reason that's given. 2, we have that angle C is congruent to angle C, and that's reflexive property. And now we can say that triangle ECF is congruent to triangle FCE, and the reason would be we have SAS, and the steps are actually 1, 2, and 1, because we proved that EC from the first triangle is congruent to FC from the second triangle, which is just the first reversed, and we proved that CF from the first triangle is congruent to CE from the first triangle, and all of that happened just in this one step here. That's why it took only one step to get both pairs of segments congruent. Okay, so now we've proven that these two triangles are congruent. Okay, CPCTC. CPCTC, just practice saying it fast. Corresponding parts of congruent triangles are congruent. So when we prove two triangles congruent, let's say by ASA or by SAS, what we've done is we've established that we have a pair of congruent angles, a pair of congruent sides, and a second pair of congruent angles, but we haven't said anything about the other two sides or the other angle. Same here, we've found 3 matching pairs of pieces of the triangle, a pair of sides, a pair of angles, and a second pair of sides, but we've said nothing about the other pair of sides and the other 2 pairs of angles. What CPCTC says is that once we've gotten the two angles congruent, we can go ahead and say that all matching parts are congruent. So if I prove, let's say, that these two triangles are congruent by SAS, well, now I can go ahead and say that, yep, these two sides must also be congruent, these two angles must be congruent, and these two angles must also be congruent. That's CPCTC, but you can't use it until you've proven two triangles congruent. Okay, so here we have circle O, center at O, and we know that OT and OS are congruent because all radii of a circle are congruent. T is complementary to MOT, and S is complementary to POS, that's given. And we have that MOT is congruent to POS, and that's because vertical angles are congruent, which means that these two angles at T and at S are also congruent because complements of congruent angles are congruent. Okay, so now by ASA, we can say that these two triangles are congruent in steps 5, 2, and 6, but now we can also say that these two sides, MO, which is this hard to see side here, and PO, this side right here, now those two are congruent because the triangles that of which they are sides are congruent, and these two are corresponding sides. So by CPCTC, we can say that these are congruent. Okay, moving right along. So these are just some things. Make sure you kind of look over these notes because they're important in terms of how you use CPCTC. Okay, so before we went up in exercise 5, we showed that the triangle, basically the triangle ABC is congruent to triangle CBA. And by CPCTC, what that means, and we did that by SAS. So we did not talk about these angles at all, but now because of CPCTC, we can say that these are two corresponding angles, so they are congruent to each other. So we've proven that in an isosceles triangle with two congruent sides, that the angles opposite those sides are congruent. Okay, so now we go down and we say, all right, let's say that all we know about this triangle is that these two angles are congruent. Okay, so what we can say is that we want to try to show that triangle ABC is congruent to triangle CBA. And so what we can say is that angle A is congruent to angle C, and angle C is congruent to angle A. So we have two pairs of congruent angles for these two triangles. And then we have that this side is congruent to itself. And so what we have is that these two triangles, that this is a true statement, and we've proven it by using ASA. And what that means is because AB and BC are corresponding parts of what are now known to be congruent triangles, they must be congruent. And so we have two new rules that we can use. If we're told that if two sides of a triangle are congruent, then we can say that the two angles opposite them are congruent. Similarly, if two angles, base angles we call them, of a triangle are congruent, then we can say that the two sides opposite them are congruent as well. And we can use this exact thing as the reason for a given statement. Okay, so in exercise 8, you were to go back to the Schoology and prove a third way of establishing two triangles are congruent, which is that if we have three pairs of corresponding sides that are congruent, the triangles will be congruent. And then as our last thing, we have that we want to show that given that triangle ABC is isosceles with AB congruent to AC, so BC is the base and G is the midpoint, which means these two sides would be congruent, that AG bisects CAB. Okay, so we have that ABC is isosceles with AB congruent to AC, and that's a given. Now we can say that angle B is congruent to angle C. The reason is that if opposite sides are congruent, then their base angles are congruent. For 3, we can say that, and so now we have that these two sides or these two angles are congruent, and we have that G is a midpoint, and that's given. And then we can say that BG is congruent to CG, and the reason is midpoint cuts segment into two congruent segments. And now we can say that triangle ABG is congruent to triangle ACG, and that would be by, so we've gotten side angle side, and that came in steps 1, we got the two sides, step 2, we got the two angles, and step 4, we got the other two sides. Now as our last step, we can say that angle BAG is congruent to angle CAG, and that would be CPCTC. It's not actually our last step. And step 7 up here would be that AG is ray AG is bisector, and the reason would be if ray cuts angle into two congruent angles, it is a bisector. Again, remember, this is a definition, so we can use it as a reason by in either direction by saying if a ray cuts an angle into two congruent angles, it is a bisector. If a ray is a bisector, it cuts an angle into two congruent parts. Okay, you can't do that typically with theorems, but you can do it with definitions.